The Raspberry Pi is one of the most popular computers of all time. From hobbyists and educators to industry and aerospace, these tiny boards are the go-to for many IoT and control applications. However, in my opinion, they're not small enough. Argo started off as a quest to make a smaller but still feature-packed Raspberry Pi board, and it all revolves around this, the CM5. The CM5 is a cut-down but equally powerful Pi 5, typically intended for embedded and industrial applications. It still provides access to all of the I/O that the Raspberry Pis are known for, whilst coming in a much smaller footprint, making it perfect for this project. There are two 100-pin board-to-board connectors on its underside, giving access to everything from PCIe and HDMI signals to the 5-volt power input needed for the Pi. Given the density of the design, I initially started with 4 layers, using the top 2 as signal and power layers, and the middle 2 as ground planes, but quickly switched to 6-layer design instead. This allowed me to add another signal layer and a 5-volt power plane too, giving a little more space to work with. Whilst I could have done this with 4 layers, without any dedicated ground planes, it wouldn't have been ideal for signal integrity, which is important to consider given our high-speed PCIe and USB signals. Of course, to make the CM5 truly portable, I designed Argo to run off battery power, using the Texas Instruments BQ25895. This is a great little integrated circuit which handles the battery charging and monitoring side of things, whilst also featuring an integrated power path circuit. On the first iteration of Argo, I tried to use the built-in 5-volt boost provided by the BQ25895, but it unfortunately didn't work as intended. It turns out, when unplugging the USB charger from the IC, there is a 40 millisecond drop-off to the battery voltage, which causes the Pi to shut down. Going back to the power path feature, when the battery is charging, the BQ25895 directly uses the 5 volts from the USB charger to power the Pi, but as this power source is removed, there is a bit of a delay for the integrated boost converter to get started, which the CM5 clearly isn't very happy with. To solve this, I opted to use an external boost converter, the TPS61022, another lovely IC from Texas Instruments. It's able to handle 5 volts or up to 8 amps, which is more than sufficient for my use case, although it's important to note that this figure is in reality limited by a battery. This was another point of contention for me, since getting even the minimum 5 volts at 3 amps is at the limit of what a single 3.7 volt lithium polymer cell can handle. Another one of Argo's defining features is the USB-C 3.0 connector. To implement it, I needed to use a USB SuperSpeed mux, as the CM5 is designed to have only a single set of transmit and receive differential pairs per USB connection. This was an issue as USB-C is reversible, so it needs 2 sets of these per port, but the mux solves this by detecting the orientation of the port and switching the output accordingly. Aside from all this, the PCB also exposes various other interfaces, including PCIe via the same pinout as the official Pi 5, both MIPI D5 connections for display and cameras, as well as some GPIO pins via stemma I2C and an SPI connector. Of course, this project wouldn't have been possible without OSHW Lab, who sponsored the manufacturing of the PCBs, so a huge thanks to them. All project files are open source on my GitHub repo and on OSHW Lab.